So everything we have worked on up to this point has been a function. What does that mean? You clearly would have like, hey, y equals. Every function has been explicitly solved for y, or f of x. Same difference. Even if it's a sine function, sine x times cosine x. It's explicitly solved for y, and we are able to, we're not going to do them, but we can apply all the rules we've learned so far on differentiation to those problems. But what you're going to find today is you don't just take derivatives of functions. You can take the derivative of any equation with respect to any variable. All right? And today, we are going to look at equations that are not or cannot be explicitly solved for y. Or if they are, they get a little complicated because they're not functions. We'll start with a simple one first, a circle. You can try to solve that for y, but is it a function? Is that a function? If I were to solve for y, wouldn't it be y squared equals 1 minus x squared? And then you'd have to do what to both sides? And as soon as you take the square root, you get two different values. Right? This is just anybody know what this is the graph of? You use it in all of trigonometry. That's not straight. You use it in all of trigonometry. It is the unit circle. It's a unit circle. It's a circle of radius 1. That's it. Centered at the origin. So that's the equation for the unit circle. So in this particular problem, it's actually easier for us to do what we call implicit differentiation. Because to solve it explicitly for y, we would end up with two different functions, the top half of the circle, the bottom half. So instead of doing that, we're going to leverage what we learned about the chain rule to solve this one. When you take the derivative of a function, you have to be told what variable you're taking it and relate it to. In other words, we are going to find, and for this section, we're going to keep it very easy. We're always going to find dy dx. In other words, we are going to only take the derivative of that equation with relation to x. The derivative would look different if we took it in relation to y. We'll do that in Tuesday's lesson. We'll start taking things related to other variables. But we want to find dy dx. So basically all I'm doing is I am going to take the derivative with relation to x of both sides. Right? So I'm taking the derivative of relation to x to both sides. Derivative, you can separate it. And again, I'm putting down way more steps than you will need to just to kind of show you the first. Well, you know how to do d dx of x squared, so that shouldn't be an issue. But then we're going to do d dx of y squared and d dx of 1. All right. Well, derivative of x squared. You all know the derivative of x squared. What is it? With relation to x is just going to be done. Okay? We'll get to that y1 in a second. You know the derivative of a constant. What's the derivative of a constant? So the one we need to talk about is this one. So here's the thing. Some of you may look at that, well, there's no x in that term, so it's considered a constant and it's 0, but no. Because when we're talking about derivatives, we're talking about a rate of change that's occurring as x changes, because I am taking dx. The thing is, y and x are so closely related that as x changes, y is also changing. So y is not a constant. It is still a variable in this problem. Because as x is changing, y is going to change. That 1, it doesn't matter what x and y is. Guess what? It's always 1. That's a constant. That's why that one went to 0. So what we're going to do is apply the chain rule. Here's the good news. The procedure is really easy. Understanding why, a little more difficult. Can you get through this whole unit without ever really understanding why? Absolutely. So I'm only going to say it once, okay? So the idea is we're definitely going to do the chain rule. And here's kind of why. So I'm doing d dx of y squared. But I don't have an x in that problem to do d dx of y squared, right? So I say, all right, well, if I take d dx of y squared, or not the y, take away the dx first. Sorry. If I first take it with relation to y, then I can take a variable. I can take a derivative, right? Because I have a y. I can do that. And then I multiply that by dy dx. Now notice, wouldn't your little y's would cancel away, correct? And doesn't that just bring you back to d dx of y squared? So I'm introducing this secondary step. So what does that look like when I actually take the derivative? Well, I can take d dy of y squared. So what do you think the derivative d dy of y squared is? Just 2y. Make sense? I don't know what dy dx is. That is what I'm trying to find in this problem. So I'm just going to write dy dx. So this becomes 2y dy dx. So here's the thing. This is why I said procedure-wise it's easy. Anytime you're taking the derivative of an x, you don't need anything else. Anytime you're taking the derivative of a y value, guess what you must follow it up with? Dy dx. And I'll even show you an easier notation to do that. All right? The reason why we can do that is we are literally just leveraging the chain rule. We're utilizing the chain rule. So this is the part you're not quite getting. Yeah, you'll be fine. All right? But I want to show you why. What lets us take d dx of y squared? It's the chain rule. By introducing, instead of calling it d dx of y squared, I first take d dy of y squared, multiply it by dy over dx. Because technically dy's cancel and they're the same thing. So what does that look like in my final problem? Well, every time I'm working on a y, I'm going to have a dy dx attached to it. But that's okay, because guess what our final step is? What did we need to do in the first place? Find dy dx. So after you take d dx of both sides of your equation, all you're going to do is solve for dy dx and get it by itself. This is a very algebra heavy problem. Not this one. This one's easy. this one's short. Not easy, short. Okay? All right, so what does that look like? Well, okay, I'm going to move the 2x. You're just solving an equation. Now you're solving an equation where this becomes the variable I need to solve for. So I'm going to take 2x, move it to the other side. This goes back to like algebra 1. So that leaves me with 2y Good so far? I'm solving for dy dx. dy dx is being multiplied by 2y. How do I? So, if I had 3x equals 15, technically, what's the step you would do? You would do what? Because you want to get x by itself. You would divide by 3. What am I going to do over here now? I'm going to divide by 2y. dy dx equals negative x over y. Negative x over y. You will then end up with a derivative that is given to you in terms of x and y. Yes. Here. Yeah. You're taking the derivative of that term with respect to x, which is why we have to use the chain rule, which is over here. So the concept behind it is you're using the chain rule. Procedural wise, anytime you're taking the derivative of a y, just do it as if it were an x, but add a dy dx. And if you don't like writing dy dx, what's another way of doing derivative of y, a shortcut method of writing it? Right, if I start with my original problem, and I want to find what's another way? We learned a lot of different ways to write derivatives, right? One of them is the d's. D this, D that. Because D represents change. What's the change in y with respect to the change in x? How much is y changing with respect to x? But what's another notation for derivative? A quick, easy one. The prime. Yeah, y prime. Y prime's really nice because I'll show you how y prime works. Forget the chain rule and all that other stuff. 2x is great. I can take the derivative of x squared because it's just an x. I can take the derivative of y squared. It's 2y. But the second I take the derivative of a y value, I attach y prime. Derivative of 1 is 0. Solve for y prime. So if you don't like writing dy dx, just write y prime. Same idea. 2y, y prime equals negative 2x. So then y prime So you tell me, well, you want to use dy dx, you want to use y prime? Does it matter? Nope, not at all. Okay, I tend to stick with y prime as I'm doing the problems because it's easier. Some people don't like y prime because their y primes, when they're writing, look just like their y's and they get confused. So that's up to you. If you are finding your y primes and your y's are looking like the same thing, use dy dx. All right, so let's do a problem. I'm just going to make one up. Could be messy, but it's okay. We're going to do it. Could be messy. All right. I'm going to use y primes. So now, remember, you still have to use all the other rules you learned, by the way. Quotient rule doesn't go away. Product rule doesn't go away. You're using chain rule. You just don't. The whole idea behind implicit differentiation is using the chain rule. Here's what you want to remember. Every time you take the derivative with a y, make sure you attach a y prime. That's all I'm going to say. So let's try it. 2y, or y squared. What's the derivative of y squared, everybody? 2y. Oh, took the derivative with a y, so I'm going to attach y prime. That's your chain rule coming into play. Or if you don't like that, write dy dx. Now, I have two variables, and those two variables are being what? Multiplied. That's called a product, which means we need to use product rule. This is where you got to be really careful, because again, if you are simply writing the letter y as is, you do not write y prime. The only time you attach a y prime is when you take the derivative of y. All right, you ready? Okay, product rule. First one, 2x. I'm just going to write it down, 2x. Now I want the derivative of y. What's the derivative of just y by itself? 1. But I need to put down, because I took the derivative of y prime. I'm not done the product rule. Now I do the opposite. What's the derivative of 2x? I did not take the derivative of y. So let me put in red what each of these are. This is d dx of y, right? 2 is d dx of 2x. So notice the only y prime is one time in that product rule. Okay, you're not done. Okay, this you needed product rule for. Okay. All right, we got to finish it now. Minus x cubed. That's whenever you see a term with just an x in it, you're like, okay, that's just what? Minus. What's the derivative of x cubed? Done. Okay, 4y cubed. I only have one variable. I don't need a product rule. I can just take the derivative. What's the derivative of 4y cubed, everybody? 12y squared. I took the derivative of a y, so I attach y prime. In green, where's my y primes? There's one, right? And there's one. You now need to rearrange your equation just solve for y prime. So get everything with a y prime on one side, get everything that doesn't have a y prime on the other side. This part is algebra 1 here. Solve for y prime. Oh, wait, there's another one. I missed one. There it is. There's 3 y primes. Sorry about that. So I have 2y y prime. I'm leaving that one on that side. Plus, I'm going to clean that up a little bit, 2x y prime. Leaving that one on that side. I'm bringing over negative 2y, and I'm bringing over 3x squared, and I'm bringing over 12y y prime to the other side, minus. All right, so all I did was take the terms that have y prime, put them all on one side of the equation, took the terms that had no y prime, put them on the other side of the equation. I got to finish solving it. What do you think I'm going to do? I'm going to make it easier, though. I'm going to factor out a single y prime. All right? It's because every term has a y prime. Take out your y prime. And now I can divide. They're not the neatest answers. That is the derivative. So that's why I like y prime, but if you don't like using y prime, just use dy dx. So let me do one where we take it just a little bit further. So I'm going to put a simpler problem up, but we're going to do a little bit more with it. So in this example, because again, these original problems are relations. They're not necessarily functions. They're crazy curves. All right, crazy curves. And what happens is, depending on the x and y, you're going to get multiple slopes at multiple values of x. So think about this for a second. Suppose I had a curve that looked like this. I'm just going to make something up. It's really probably not going to be realistic, but it's all right. Right? Suppose I had a curve that looks like that. Do you see that curve? If this is my x value, how many different slopes am I going to have at x? Well, there's going to be a slope there, right? There's going to be a slope there, and there's going to be a slope up there. So you're gonna end up with multiple slopes sometimes at a given x, because you're no longer dealing with functions right now. Okay, you're no longer dealing with the function. And there's a problem on the lab you'll go through. And how do we end up with that? Well, your derivative is going to have these squares in it, and you know when you solve quadratics, you end up with multiple x values. So you're going to end up with these multiple values. So just keep that in mind. All right, so let's do one problem where we do take it all the way through. So let's find the slope of a curve. So notice they're not called a function anymore. And the curve I'm going to do is 2x plus y to the 1/3 equals y. You have to be given the point you want to find that slope at. So it's going to be at, we're going to use 4, 4. So here's the thing. Second you hear the word slope and you've got a curve like that, you're doing a derivative. You just have to do it. That's how you start. So we're going to start by doing implicit differentiation on that particular problem. Okay? We definitely have to do the derivative. So I need to do d dx of both sides of the equation. So let's take a look at that. This side first. You are going to end up using even more chain rule here. All right. So think something, I'm not going to substitute my u's in anymore. So think something is being raised to the 1/3 power. How do I take the derivative? Where does the 1/3 move to? Right? If you just had x to the 1/3, wouldn't it be 1/3 x to the minus 2/3? Right? We're going to do the same thing. All right, so it's 2 times 1/3 this to the minus 2/3. But I now need to take the derivative of what's inside of that parenthesis. That's where your chain rule comes in. I now need to multiply it by the derivative of what's inside. So start with x. What's the derivative of x, everybody? 1, just 1. What's the derivative of y? It's 1, but because it's a derivative, and that's what you're saying to yourself. Hear those words in your head. I am now taking the derivative of y. So what do I need? I know it's only a 1, but it's 1 times y prime. 1 times y prime. Oh, what's the derivative of y on the other side? Yeah, it's just y prime. So here's where you need to be careful, because this is where you're going to get caught up in the algebra, right? This is where I don't want you to get caught up in the algebra, but you're probably going to get caught up in the algebra. So now look at that problem. Yeah, all right. So what do we have? Take this and multiply it by everything inside. Well, the first thing is 1. I'm just multiplying all of that by 1. So it's 2/3 x plus y to the negative 2/3 times 1, and then plus 2/3 x plus y to the negative 2/3 times y prime equals y prime. Okay, this is just algebra. I took this whole thing, distributed it, because I can't move anything over to the other side of the equation until I do that. So now, let's go ahead and keep 2/3. Oops, not equal, sorry. Minus. We're going to move this whole piece over to that side of the equation. Okay, you're going to follow. I know you don't like the algebra, but this is what we got to do. You know, we have to use everything you've learned in every algebra course you ever took. Factor out your y prime. You're always going to be factoring out your y prime. And divide. So get caught up to there. You can simplify that or you can leave it. To simplify it, you can actually multiply everything by 3. X plus y to the 2/3. But I don't, you'll probably get more messed up in trying to simplify that than if we just plug the numbers in there and work it through. Does that make sense? Yeah. Okay, so we want to know the slope at 4, 4. Well, when we were doing functions and everything was in terms of y, all you had to plug in was the x. This time you have to plug in what? Both x and y. That's it. It will actually work out. Let's do it. Just plug in your x and y to get your slope. So y prime equals, believe it or not, 4 plus 4 . The reason it works is because what's 4 plus 4? Can you take the cubed root of 8? You can. That's why this one kind of works out nice and neat. You're not going to get numbers that don't work out. Okay? the 4, 4 was picked on purpose because it will work out really nice in the problem. So go ahead and do all the math. So that's 2/3. So 8 to the negative 2/3 is 1 over 8 to the positive 2/3. What's cubed root of 8? 2. What's 2 squared? It's 1/4. Comes out to 1/4. So it's 2/3 times 1/4. What's 2/3 times 1/4? It's 2, 4 cancels, 1/2. It's 1/6 over 1 minus 1/6. I'm just working out fractions in my head, not doing anything special here, right? 1 minus 1/6 is negative 5/6. Oh, that's 1/6 times negative 6/5. Answer is negative 1/5. Done. That's just fraction arithmetic. It's to get rid of that. Pretend that negative was never there. 1 minus 1/6 is 5/6, not negative 5/6. Don't know why I did that. Because it's 6 over 6. 6 over 6 minus 1 over 6 is 5/6, not negative. So it's positive 1/5. I was like, what was I doing? All right. So you know the slope. Don't forget, with the slope, you can write an equation of a line. You have the 0.44. So don't forget that stuff, too, once you have your slope. So the slope is 1/5. All right. If you were asked for the equation of the tangent line, you would do y minus 4 equals 1/5. And you can get that equation too. This implicit differentiation can be used even when there's trig functions in the problem. So let's take a look at one of those. All right, let's do sine x plus sine y equals y. Because the one I just gave you was a lot. I know that. It had a lot of algebra. So they will have a lot of algebra in them. Some of them won't. Some will just have, you know. It's also kind of fun to play with some of these graphs to see what sine x plus sine y equals y looks like, and then you can do the graph, and that can help you in some ways too. All right, so you take the derivative of each piece with respect to x. Sine x just has an x in it. What's the derivative of sine x, everybody? Done. Sine y, I'm taking the derivative of something with a y in it. Keep that in mind. What's the derivative of sine again? Oh, it's going to be cosine y. But then I have to multiply it by y prime. Oh, what's the derivative of y? 1 y prime. See that? All of a sudden you're like, oh, well, this one's not that bad. See? And you think the ones with the trig functions in it are going to be the hardest problems. Not always. I'm going to do it this way. Doesn't matter. Cosine y times y prime minus y prime equals negative. Okay. You got to get all the terms with the y prime on one side. So this part's pretty standard. Get all the terms with the y prime on one side, every other term on the other side, and factor out y prime. Did I move everything correctly? Yeah. I just did it that way. You can do it the other way. Doesn't matter. The only difference is your signs will be a little bit, it'll be the same answer in the end. You'll have an opposite sign, and then the subtraction would be the opposite. But it's all the same. So take out my y prime. Minus 1. So what does y prime equal? Negative cosine x. That's it. If you factored it the other way, right? And I don't mean factored, I'm sorry. If you moved this one to this side, right? You'd have y prime minus. It would actually look like this. Okay, they are the same answer. Recognize that. They're exactly the same. Because if I take this negative and apply it down here, it makes the cosine y negative and the 1 positive. That's all. It's the same answer. Okay, so that was my big lesson. Now you get 2 mini lessons. Okay? So I can save the really big lesson for next Tuesday. I'm going to keep it on the same video because you know what happens when I try to switch out. But I do like to switch it to different notes. And what I want to do here is actually combine 2 sections. One that we kind of skipped over a little bit. Yeah, we're going to combine 3/9 and 3/10. Which is derivatives of logs and inverse trig functions. Derivatives of logs and inverse trig functions. So here's the good news. You already know I already gave you that one, right? The question is why? So let's suppose I didn't have an e to the x. Because e to the x is a very, very special number. E is a very, very special number. It is so unique, it is the only thing whose derivative is itself, is e to the x. What if I didn't have e to the x? What if I had 3 to the x. And what if I wanted d dx of 3 to the x? Yeah, that is not going to be 3 to the x. Well, it's going to be part of it. All right, this is where the natural log has to come into play. So with these particular functions, you are going to literally add this to your list of you need to memorize these derivatives. We're not going to go over proving them. I'd rather spend more time just having you guys work on your lab than proving them. Some of these you're just going to memorize. So yes, it is true. It starts off 3 to the x. But then you're going to multiply it by the natural log of 3. So in general form, d dx of any base, that b represents any base whatsoever to an x power, equals that base to the x power times ln of the base itself. E to the x happens to be a special case. E to the x follows this derivative. Yes?
So you do this rule
Raising anything to an exponent, not a variable. X to the x is a special case. We get that into later, of course. Yeah, it actually also works for e to the x. Can you see that? So watch. If I apply this idea to e to the x, that tells me it's e to the x times the natural log of e. What do you remember about your logs? Anybody remember what the natural log of e is? 1. So yeah, it applies to anything, any constant, any base raised to an x. Constant. The b has to be a constant. E is a constant, which equals e to the x times 1. So e to the x just happens to be a special case of the derivative of any base raised to the x power. All right? So this one needs to be memorized. Put a big red star. I'll put a big red star. You may not have red. Okay? You need to memorize that one. The other one is, we've kind of alluded to this one. Some of you had looked it up. The next one is d dx of the natural log. Which is basically 1 over x. That one's kind of and you can kind of see this in their graphs, because if you recall, the natural log graph goes like this. So a couple things I want you to notice about the natural log graph. If we were to talk about the derivative function of that graph, right? Remember, one of the things you want to pay attention to is the relationship between a function and its derivative function. So if you talk about any point on the natural log graph, what could you tell me about the slope in general of any point along the natural log graph? Whether I'm here, 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 my slope is always what? My slope is always positive. So that means the derivative function is all above the x-axis. Okay? It's going to be above the x-axis. The other thing is there any point in a natural log function, y equals ln x, where you are going to end up with a 0 slope. No. So not only is it always positive, it's also never going to touch 0. And they happen to be equal to each other. When does the derivative and the function equal each other? At e, which is about 2.718, something like that. So right around, here somewhere. So your graph is kind of that. There's your derivative for your natural log graph. It's never going to touch 0, and it ends up being the graph of 1/x. Okay? So just some things to play around with. But that is just another one I want you to memorize. Other than that, as far as your logs go, we've talked about the natural log, but you're all familiar that the natural log is simply a special case, right, of log. Right? So what if I had d dx for the next one? Okay, not all logs are natural logs, right? When you first start learning logs, you didn't start learning ln, you started learning log. So the natural log, the derivative of log any base is kind of a combination. And again, this is another one, I'm just going to give it to you. It's just 1/x times ln of the base. We're not going to do a lot with logarithms, but you should know it. You should know it. So for this one, if you were given y equals, or let's do f of x, log 5. Okay, so when you are applying these derivative rules, keep in mind, product rules still exist, quotient rules still exist, chain rules still exist when you're doing these. So for this particular problem, I can start off with recognizing, yeah, I've got a log, but don't I have a function inside of it? So if you want to treat this, when you look at something like this, yes, you're going to apply the derivative of log base, log b of x. But if you're going to break it up and use your u's, you're going to let u equal to x plus 1, right? So your y becomes log 5 of u, all right? You don't have to, again, once you start using the chain rule a lot, you don't have to keep writing out what your u is, but it is helpful in the beginning. So, all right, du dx is just 2. Plus it breaks it down and makes it easier for you to find the derivatives. And we just learned that dy with respect to u in this case is going to be 1 over. So just kind of follow the pattern here. This x comes from this x, so this is a u in this problem. The natural log of the base, this is a base 5. And you're just going to multiply them together. So f prime of x is now, okay, I have my 2 times 1 over. I'm not going to write u, though. What did u equal? 2x plus 1 times ln of 5. I mean, I would clean it up and just write it like this. There you go. That's it. That's it. So all I'm giving you here is just a couple more, and I wanted to give them to you now so you can start that memorization of them, right? Just a couple more to memorize. The same with the inverse trig functions. We are not going to use a lot. So here's what I'd say. Yeah, you need to know this, you need to know that, and you need to know the general case up here, right? So I gave you 3 more to make sure you know. You already knew e to the x. But now think of e to the x as a special case. You'll remember, oh, I just take ln of whatever the base is. So you've got these 2. Inverse trig functions. Last one. I'm not going to make you memorize a lot of those, but you're going to work on a lab next week. We're going to do them. So the derivative of the inverse trig functions. Do you recall your inverse trig functions? Okay, if this is classic sine, right? Right? The inverse function occurs when you switch your x and y values. So instead of it being, it kind of goes like, it's kind of like that, I think. I'm trying to get the graph of it correct. Yeah. Yeah, it's kind of like that. So the inverse functions, your x and y's are switched. Again, I'm not going to go through the proofs. I just want you to have it so you can apply it if I give you the functions. These are a little bit more complicated. If you do want to see where they come from, they are on page 218. They go through a nice little, it's not bad actually, because you can use implicit for the sign, makes it kind of nice. So the idea is, if this is the original function, y equals sine x, your inverse function, right, is x equals sine y. You agree with that? That's the inverse function. So I can go ahead and take use implicit. You just learned implicit differentiations. Let's use implicit differentiation on that, and let's go ahead and, because it's not a function, because if it's going to squiggle up and down the y, it's not going to be a function. So we're going to use implicit differentiation. Oh, what's the derivative of x? 1. What's the derivative of sine y? Right? Oh, so y prime equals 1 over cosine of y. And then it gets, so this is what's really cool about proofs, is you can pull from anywhere to get a proof the way you want it to be. So suppose I wanted this y prime to be in terms of x. You're probably thinking, well, how the heck would you get that in terms of x? Well, we are all aware, right? You agree with that? Everyone agree with that? So if you agree with that, would you agree that cosine y itself would equal the plus minus square root of 1 minus sine squared y. Would you agree with that? Just a little algebra. Just rearranged it. Okay? Oh. Well, what did I just define sine y to be? What's sine y itself equal to? X. So since sine y is equal to x, wouldn't cosine y be the square root of 1 minus x squared? Okay? We are only going to deal with it. When you are dealing with these inverse functions, you only go between negative pi over 2 and pi over 2, so you can drop the plus minus. That's fine. So y prime equals 1 over the square root of 1 minus x squared. And that is your first inverse trig function. So here they are. D dx of sine that's the first one. I'm not going to do them all with you, but you can get them using implicit differentiation. And d dx done in similar fashion. It looks like that. We are going to restrict all of these to x being from -1 to 1, but don't worry about that. You don't need to worry about that when you're working out problems. Okay, d dx of tangent. This one's easy. Cotangent is simply negative 1 over 1 plus x squared. This one right here is one of the most used derivatives in calculus. So if you're moving on to Calc 2, if you don't memorize any of these, memorize that one. Okay. That is actually one of the most useful ones. And then the last two. So you see the one I haven't read? That is the only one I would possibly give you on the test. I'm not going to make you memorize all 6 of these. All right, when you do the lab next week, you'll have to pull this sheet out. You'll have to use them. And you have to use them when you take derivatives. But I'm not going to make you memorize them all. I don't want to drive you crazy, except for the tan one, because that is one you'll use a lot. Yeah. Yeah, it's just you actually can't plug in anything less than, you can't plug in a negative just because of the way the function is. But you don't need to worry about it when you're using it. It's more for like defining purposes. One example, and then we're moving on to the lab. So let's just do, okay, how would I use this? I want one that's not too crazy. I guess we'll just do this one. So here we go. if f of x equaled x times tan inverse of x over 2, how would I find that derivative? Okay. F of x equals x tan inverse of x over 2. So notice, throughout today's lesson, quite a few times we've practiced the product rule. We're going to practice it again right now. You know, you need to apply the product rule first. Product rule states, however you want to do it, doesn't matter. You want to start by taking the derivative of x. Let's take the derivative of x. Derivative of x is just 1. And then copy exactly what's there. Do the opposite. Write down your x. And now I need the derivative of tan of x over 2. We're going to use chain rule because this is not just this. I didn't make it easy and just put x. I put 1/2 x. That's just a little tiny chain rule. Not much. Not much. So how do I take the derivative of that? I apply what I have in the red rectangle. That says, okay, I start with 1 over (1) plus, notice, I don't put x squared. What is my entire x value? It's x over 2. It's not just x. Does everybody see that? This says x. This means whatever you're taking the inverse, whatever that value is. In this case, my value is x over 2. So it's the x over 2 that I'm squaring. So that becomes x over 2 squared. Now I got to apply that chain rule, which says now I need to multiply that by the derivative of 1/2 x. What's the derivative of 1/2 x? What's the derivative of x over 2? Yeah, just a half. And this comes from chain rule, where u is actually x over 2 and y is tan. My pen won't stretch. That's where I got that from. I applied the chain rule there. I can clean that up. I can absolutely clean that up a little. Well, I'm going to clean up the first part by not putting the 1 there. So see this piece here? You can totally clean that up. That is actually, what does that look like? There's an x over 1 plus x squared over 4 times a half. So this is like a half. That becomes an eighth. Let's just make it that actually becomes 2x over 4 plus x squared. This reduces to 2x just by can multiply it through 1/2 plus x squared over 8, and then multiply everything by 8, and then simplify it. And that's what you end up with. Yeah, because you end up with 8x over 4 plus something like that. If you do the math, that'll clean up. All right. So you've learned a couple more rules. Okay. And